Hello everyone, welcome to our session. We're going to talk about lifecycle operations of Kubernetes clusters at the edge, and we're starting to make this a little bit interactive with you. Now, my name is Atanas. There we have Ivo. We're going to be your hosts today. We're both part of the Edge team, and we've been working on the lifecycle for the past year or so. So we might know a thing or two about it, but we'll see in a bit. All right. Now, before starting with the agenda, I'm going to make this, again, a little interactive. So how familiar are you with Kubernetes? Let's raise your hands if you're familiar with it. OK, very good, very good, very good. And how many of you are familiar with this SUSE Edge suite, the Edge product? Some hands. All right. So before we start, we'll briefly cover that. Now, the SUSE Edge product consists of different components that are tightly integrated together, validated, verified, and established to be working together. Now, we have, let's say, 3 different layers. We start with the operating system, namely SLI Micro, or rather SUSE Linux Micro right now. Then we have our Kubernetes layer, so K3s and RK2 respectively, as well as additional core components that we publish with those on top. So that would be Rancher Prime, New Vector, Longhorn, and many others. The full list you can check out on our documentation. Now, the agenda is going to cover how we're going to actually be able to upgrade an Edge platform from one version to the next. It will include our motivation, our tool that we developed for this purpose, as well as a demonstration, which is not going to be live, it is going to be a recording.
I'm not that brave.
Yeah, we are not that brave, and it would also take just a lot of time. Now, when it comes to deployment options, we have largely identified 3 different deployment paradigms. So we have directed network provisioning, phone home network provisioning, and image-based provisioning. The first one, we basically talk about cluster API. So we have non-hardware and a means of accessing the bare metal servers. So we are able to provision and lifecycle our infrastructure using MetalCube and cluster API. Now, for the second one, we have the phone home, which is based on technology that many of you might be familiar with, which is Elemental. So you have a centralized server, in this case Rancher Prime, which serves as the acting management layer, and eventually you have your machines go back to Rancher. Finally, we have the image-based provisioning, which is something that we talk about a lot lately with Edge Image Builder. So this is our means of creating a self-install ISO or raw image containing all of the different technologies that you need to provision infrastructure layer on the edge environments. So it will fully establish Kubernetes cluster with all its necessary components, configurations, as well as many different means that you need on your edge environments. Mainly, when we talk about image-based provisioning, we also talk about air-gapped environments. So we have something which is fully disconnected or partially. So let's say it's either fully disconnected or something that has low connectivity. Now, after we have this, we'll establish our common ground when it comes to the different cluster types. So we have basically 3 different ones. So standalone clusters, meaning that the customer workloads are running on a separate Kubernetes cluster. This could be single node, this could be multi-node. However, the main differentiator here is that this is not managed by anything. So it is deployed somewhere and it just runs. Now, what we usually do is we bootstrap these with that technology that we just mentioned, so Edge Image Builder. The second cluster type is management clusters. So what we have here is a special scenario for standalone clusters, which are almost the same. So we again use Edge Image Builder to bootstrap and provision these. However, these also run some sort of centralized management infrastructure. This can be cluster API and or rancher with Elemental. Finally, we have our downstream clusters. So once you have management clusters, this means that you want to eventually establish, provision, and fully lifecycle other clusters. So on the management clusters, we don't have any sort of customer workloads. We only have the necessary infrastructure that is obviously required to provision downstream clusters, which are then running the different customer workloads. Downstream clusters can be provisioned in 3 different ways. So we have the ones that are based on the first deployment paradigm. So those are largely provisioned and managed via cluster API. And in the Edge solution, we use a combination between cluster API and Metal Cubed. Now, for the second use case is what we had in the second deployment paradigm, which is the calling home one. So we have Elemental running on the management cluster, and all of these machines are somehow equipped to know that they have to, they basically carry the registration configuration that is necessary to be imported into rancher. And finally, we have the standalone case, which is a cluster that you normally deploy and provision. However, at some point in time, you import into rancher. So you see it into rancher, but it is not provisioned by cluster API or via Elemental. Now, we have all these different things. So how do we want to manage their lifecycle? We came up with some sort of idea. So if we have some sort of a concept called Lifecycle Manager right in the middle, then we have to think about two or maybe 3 different things. So to the left, you see the upgrade order. What do we want to achieve here is to be able to upgrade our operating system layer first, so all of the different nodes. And once this is done, only then we should move over to the Kubernetes layer. So namely K3s or RK2. Finally, we have the additional components, which I previously briefly mentioned, in the name of rancher, Elemental, new vector, and so on and so forth. So once we have largely established this part, we need to figure out, well, what do we exactly need in order to bootstrap this process? So to the right, you see that we basically need 2 different things. So first is the release blueprint, which contains all the different components, rather the versions of all the different components consisting of a SUSE Edge version, as well as to the bottom, you see the upgrade trigger. So how the user does actually trigger the upgrade process. Now, when we move on, that's our solution. So we came up with something called the SUSE Edge Upgrade Controller. The name might not be the best one, but we'll eventually figure out how to improve that. So what we have here. So this is cloud native, Kubernetes native, implemented as Kubernetes operator. It will upgrade the SUSE Edge infrastructure platform that we briefly mentioned earlier. So it consists of the operating system, SUSE Linux Micro, then the Kubernetes layer, and then those additional core components. In order to achieve that, this new Kubernetes operator is going to extend the Kubernetes API via the following CRD extensions, custom resource definitions. So we have the 2 different concepts that we saw from the previous slide. The release manifest, which is something going to be represented, let's say, as a read-only database, in quotes, containing all the different versions of the components. And then we have the upgrade plan, or rather the trigger of the upgrade process. So this is the thing that is going to eventually be created by the user. Now, before jumping onto these, let's mention some advantages and limitations of this tooling. So advantages, first, in the name of the, in the spirit of SUSE, it is completely open source. You can try it out even today. Feel free to go back to your room, set up your Edge environment, and trigger the upgrade controller. Now, it is Kubernetes native, so obviously following the best practices, the technologies, the supply chain that comes with building something running in Kubernetes. It hides the operational complexity, so this is eventually a single centralized point of tooling which does the upgrade for us. We don't have to do any manual steps. We don't have to do anything pretty much aside from creating a simple, rather triggering the simple upgrade procedure by applying a custom resource on our cluster. Simple cluster maintenance. What we mean here is that, well, if you were to do all of these upgrade steps yourself, you would have a lot of implications on complexity, on security, on pretty much everything. You would have to, let's say, for operating system, go through the different nodes, maybe run some sort of custom scripting to update your packages or do a migration and so on and so forth. So this is a lot of work. Finally, it reuses existing SUSE tooling. This is something that we're going to touch on later, but basically we don't want to reinvent the wheel. We want to use as much as possible from what we currently have in the SUSE suite, so this is definitely something that we do. As far as limitations go, it is x86 only right now, and this is, let's say, a small limitation, something that we can easily get rid of eventually. We just need to figure out which of our core components can run on ARM and which not. The other limitations are a little bit bigger, let's say, so to speak. So the first one is that it will not work on downstream. When we talk about downstream clusters, we only reference those the calling home ones from Elemental, as well as those provisioned via Cluster API. We have limitations there just because there are some sort of things that we need to mitigate, basically bridge the gap between how Cluster API currently manages its infrastructure, namely treating the infrastructure as immutable. This is going to be mitigated by an open source, obviously upstream proposal about in-place updates. So as soon as that is ready, we should be able to have something about it. Now, the final limitation is that this is not going to work for air-gapped environments right now. So when it comes to air-gapped environments, what we would usually have to do is gather all the different artifacts. And for example, if those are container images, Helm charts, and so on and so forth, we would have to set up some sort of registry. Now, this embedded registry would have to be brought to the cluster, and then our upgrade procedure would work. But right now, this is not so simple to achieve, and in the first version, we don't have it. With that, I'll be handing over to Ivo to dive into the specifics.
All right. So, first of all, hello, all of you. First, let's look at the custom resources that Atanas touched briefly on, starting with the release manifests. As he said, it's essentially a database or a blueprint showcasing all of the components that actually make up a specific Edge release. The release manifest itself is actually built for each release, for each Edge release, and is intended to be deployed by the upgrade controller, easing the configuration burden on the user. He does not have to care about the release manifest. He just needs to specify an Edge version, and the upgrade controller will deploy the release manifest and start working with it. On the right, you can see an extremely, I would say, stripped down version of the release manifest, but at its core, it holds information about two things. The first, as I already hinted on, is actually the Edge release version that this release manifest relates to. The second one are the actual components and their versions related to the Edge release that this release manifest actually describes. And in a nutshell, that's what a release manifest is. Now, moving further, Atanas, if you can just change the slides. Moving further to the upgrade plan, as again Atanas mentioned, the upgrade plan is essentially the only user-facing resource that the user actually works, configures, and deploys. It acts as a trigger for the upgrade process and essentially describes or instructs the upgrade controller on the specifics in terms of upgrades that need to happen for a specific environment. So the main configuration here, again, on the right we see the full, this time, upgrade plan as of this moment. The only, I should say, the only mandatory property here is the release version, which directly relates to the release manifest. How it relates to it, I will explain the next slide, but for now, we'll just leave it at that. Now, the other two configurations are optional and essentially give the user the possibility to, first of all, for HA clusters, disable the default node drain that the upgrade controller does for operating system and Kubernetes upgrades. And the other functionality or configuration mechanism that it introduces is the ability to configure custom values for SUSE core Helm charts, because a specific Helm chart might require some environment-specific configurations in order for it to be functioning after an upgrade. Now, moving further to the next slide, where now that we understand what are the core resources that the upgrade controller works with, now let's just look at how it works with those resources and what is its general upgrade workflow. So as Atanas mentioned, the only thing that the user needs to do is just deploy the upgrade plan, and the upgrade controller, of course, it is a Kubernetes operator. It has a reconciler inside of it. It immediately detects the upgrade plan. It takes the release version, and based on the release version, searches for a release manifest inside of the cluster that it can use. If it does not find a release manifest in the cluster, it will create a workload that will pull the release manifest image and deploy the release manifest resource onto the cluster. Once the release manifest itself is deployed, the upgrade controller can then begin its upgrade process. And the upgrade process itself has a very specific flow. It first starts with an operating system upgrade. It then continues to a Kubernetes upgrade only when the operating system upgrade is finished. And finally, when both the operating system and the Kubernetes upgrade have finished, does it start upgrading the SUSE core Helm charts. Now, building upon what Atanas said about the fact that the upgrade controller actually uses SUSE tooling in order to achieve all of this upgrade automation, here at the bottom, you can actually see the two SUSE tools that the upgrade controller actually uses, which are the System Upgrade Controller, or SUC for short, and the Helm controller. Just very briefly, for those of you that are not aware of these tools, the System Upgrade Controller is essentially a Kubernetes operator that is capable of deploying workloads onto a specific set of nodes based on a configuration that is provided through a custom resource called a plan. So kind of similar to what the Upgrade Controller does. And the Helm controller is a Kubernetes native application that is capable of managing Helm charts and comes by default with the K3s and RK2 distributions. Moving a bit back to the whole upgrade process, now that we know what components are used under the hood, the upgrade controller, first of all, we'll start as I previously said, the operating system upgrade. It will do this by creating this system upgrade controller plan that instructs the system upgrade controller what workload does it need to deploy and how what this workload will run in order to upgrade the operating system. The operating system itself currently can be upgraded, or I should better say there are two types of operating system upgrade that the upgrade controller supports. The first one is just a pure package upgrade. This happens when the environment that the upgrade is applied on, the operating system in this environment, is the same as the operating system defined in the release manifest. Their version is the same. So then we just do a package upgrade and just upgrade the packages to their latest versions. If there is a mismatch, so the operating system version in the release manifest is larger than the one that's currently on the system, then we do a migration, and after that we upgrade all the packages again. Now, that said, this is a transactional operation, so after either type of upgrade has finished, we will perform a node restart in order to ensure that these upgrades have taken effect. And once the operating system upgrade finishes, pretty much we do the same for the Kubernetes upgrade. We create an SUSE one. SUSE deploys a workload. This workload is actually performing the Kubernetes upgrade by utilizing ranchers, K3s, and RKE to upgrade images, which essentially ship K3s or RKE to binary within the image. And once this image is run on the system, the RKE2 or K3s binary that is in the image will replace the RKE2 or K3s binary that is running on the operating system. This essentially will trigger the Kubernetes upgrade. Now, an important note here is that we don't just mark a Kubernetes upgrade as succeeded when we just change the binary and say, okay, everything is okay. We also validate that each Kubernetes distribution core component is in a running state and is running the versions that are expected to be run for the specific Kubernetes distribution version. And essentially, the same thing, Kubernetes upgrade has finished. We move to Helm chart upgrades, where for Helm chart upgrades, we use the Helm controller. So our tool supports upgrading both Helm charts deployed through the Helm chart controller method, so a Helm chart resource that actually defines the chart and the Helm controller deploys it, and for Helm charts that have been deployed with the Helm CLI, so just a plain Helm install. Both of them are supported and are essentially diverge into a same point, which is the Helm controller, and actually the Helm controller does the upgrade. That's a very rough and frankly dry explanation of this whole workflow. But the last important thing here is that the whole upgrade process is described, its state is described in the upgrade plan status. So each component status, upgrade status, is described in the upgrade plan, and the user again only interacts with a single resource, deploying it and then just monitoring its status, whether to get information for the state of the upgrade process. Now, moving further, as I previously mentioned, I am not brave, so I have prepared a demo for you. Hopefully, I will not be able to break a demo, but you never know. And I broke a demo because I can't do a full screen on the demo. Okay, nevertheless, do you see it okay? Yeah. Fine. So a couple of words before I started. What I'm going to showcase here is upgrading a single node management cluster that is running the SUSE Edge platform version 3.1.1. And we're going to upgrade it to 3.2.0. So naturally, we will first start by showcasing the current state of the environment. So we can see that we're running a single node. This node is running RKE2 130.5, and it's running SUSE Linux Micro 6.0. The operating system has never been upgraded, so it has a lot of packages, which you're going to see now, that are in need of an upgrade. That's a great showcase because later on, they won't be there. They will be upgraded. Also, the Helm charts, the SUSE core Helm charts that are present on the machine are Rancher, Longhorn, the Rancher Turtles application, and the Metal Cubed application. Here, please take note of their versions. We're going to upgrade them as well because they're all considered more or less core Edge charts. Now that we have an idea of the state of the current environment, we then just need to deploy the upgrade controller. The upgrade controller, oh man. Right. So the upgrade controller is shipped through a Helm chart that is wrapped in an OCI image. So here we just install the upgrade controller. Yay, it's installed. We're going to go and very quickly validate that the upgrade controller spot is running. It has some logs. The logs don't have any errors. Come on, show the logs. The logs don't have any errors, so we're very happy and we're ready to start the upgrade process. So we need to define our upgrade plan. And how does our upgrade plan look? Extremely simple. We just specify the release version or the target that we want to upgrade our environment to. As I said, we're upgrading to the Edge 3.2.0 version. So as previously mentioned, the upgrade controller will look for a release manifest with this version. Here we showcase that there is no such release manifest, meaning that the upgrade controller will deploy the release manifest itself. And that's exactly the next step. Come on. Yay. So at the top, we're going to deploy the upgrade plan. At the bottom, we're watching for the pods in the upgrade controller system. And in the middle, we're watching for the deployed release manifests. Immediately when we deploy the upgrade plan, we can see that a workload is deployed that will actually deploy the release manifest for us in just a couple of seconds. Here it is. Now, once the release manifest is deployed, the upgrade process will be triggered. Before looking at the upgrade process, we're actually going to take a look at what the upgrade controller deployed actually. I am saying a lot of actually. So we can see that the release manifest is for the version 3.2.0. We can see that the RK2 version that relates to this Edge version is 131.3, and we can see that the operating system version is again SliMicro 6.0, which essentially means that when we do an operating system upgrade, we are going to do a package update. We are not going to do a migration, we're going to do a package update. And now we're going to showcase all the charts that are related to this specific, all the charts and their versions that are related to this specific Edge release. Now, as you remember, I showcased the Rancher, Longhorn, and MetalCubed, and Rancher Turtles charts were deployed here. So this means that Rancher will be deployed, for instance, to 210.1, Longhorn will be 17.2, MetalCubed will be 0.90, and the Rancher Turtles application would be 0.41. Now that we just had a rough overview of the release manifest, just to give you a better understanding of what is in a release manifest, we're just very quickly going to show the full spec of the release manifest. There is a lot of information here that is only needed by the upgrade controller that the user really does not have much value in. So this is just for your context. This is the full release manifest. Based on it, the upgrade controller will take information for each component, and based on that, know how to upgrade this component. Now, the release manifest has been deployed. What will happen now? The upgrade controller will create a system upgrade controller plan for the operating system upgrade. The system upgrade controller will create a pod that will actually run the upgrade, which is exactly what happens here. At the bottom, we create the upgrade plan, the system upgrade controller plan. The system upgrade controller in the middle creates the pod. And here at the top, we see that we have upgraded the status of the operating system upgrade inside of the upgrade plan. So essentially, that's the whole workflow, and this will be the whole workflow both for the operating system and for the Kubernetes upgrades. For the Helm charts, it will be a bit different, and I'm going to show it a bit later on. So now, just very quick, we should take a look at how the system upgrade controller actually looks like. So this is its status. It is just applied on the specific node, and it is shipping the 3.2.0 release version. Now, the spec is a bit more interesting, and it describes not a lot of information, but yeah, a lot of information. And the most important thing here is the upgrade section, which essentially specifies the image that the workload node that the system upgrade controller will create, and what script it will run in this case. And under the node selector, it specifies on which nodes for which nodes does this workload need to be deployed to in order to do whatever work it needs to do. For instance, here, the operating system upgrade. Now, next, we're going to take a look at the logs of the workload itself. As I mentioned previously, this is a transactional command, so we're just going to see the logs of a transactional update output that is currently running for all the packages that we previously saw are in need of an upgrade. As I said, transactional updates, in order for them to take effect, we need to restart the node. So this is exactly what will happen once the pod finishes its execution. And after the node restarts, the operating system will be marked as succeeded, and the Kubernetes upgrade will begin. Yep, here we saw that the reboot happened. Now, here in just a second, we will see that the operating system succeeded here, and we see that the Kubernetes distribution began to be in progress, so its upgrade began. And here again, we see the system upgrade controller plan being created for the RK2 upgrade, and we see the workload that is related to this RK2 upgrade. Moving a bit further, we're now looking at the plan. We're again going to look at its status. The status will be pretty much the same as the operating system plan on which node, just the latest version is different because we're applying something different. And the status and the spec itself would be would not be that large because we're not running such a complex operation as upgrading an operating system. We're essentially, as I previously said, we're upgrading the Kubernetes distribution using the Rancher RK2, in this case, upgrade image. Now, as I previously said, apart from changing the RK2 binary as part of the Kubernetes upgrade, we are also validating that all of its core components are up and running before marking the operation as successful. And this is exactly what is going to be shown in a couple of seconds. Yep, here it is. So in the middle, you can see all the core components that are managed by the Helm controller and that are related to the RK2 distribution. At the top, you can see that we are changing the informational message for the status of the upgrade plan, or more specifically for the status of the Kubernetes upgrade, and we're specifying which core component are we waiting for to be upgraded before we can specify that everything is running. And now, all the core components are completed, and we're going to mark the Kubernetes distribution as upgraded. When this happens, we essentially proceed to upgrading Helm charts. Now, Helm charts are upgraded sequentially, and here I'm just showcasing one, but the upgrades is essentially the same. Let me just very quickly pause here. So at the bottom, we're seeing, first of all, we're upgrading Longhorn. At the bottom, we're seeing both the Longhorn CRD and the Longhorn Helm charts. Longhorn CRD is there because it is a dependency for the Longhorn chart, and it needs to be upgraded first before the actual chart. So what will happen is the upgrade controller is going to edit the Longhorn CRD chart first. It's going to edit its version, which happened right now. And the Helm controller will detect this change in its custom resource, and it will create a Helm install job that will create a pod that will actually run the Helm upgrade command for us. So we're essentially leveraging the functionality that the Helm control offers to us by default, or not reinventing the wheel. So we see that the CRD has been upgraded, and immediately we did the same thing for the Longhorn Helm chart. Both of them completed, so we mark the Helm chart as succeeded. As simple as that. Now, moving a bit further, just to see the logs of the Helm install Longhorn, so that you know that I'm not lying to you. The logs, pretty much as I said, just showcase the Helm upgrade command. We're just doing a simple Helm upgrade for the version. And this, as I previously said, is done for all of the Helm charts. So once all the Helm charts are upgraded, once the operating system upgrade is upgraded, the Kubernetes system is upgraded, we are very happy nothing broke. How can we check that the upgrade process has actually finished successfully? We can check by looking at the upgrade controller status. So here, it's just a very quick showcase of how a successful status would look like for the upgrade controller. So we can see the operating system is upgraded, we can see the Kubernetes system is succeeded, and all of the Helm charts that are related to the specific environment. Now, you may see that some charts are marked as skipped. That's because they're just not on the cluster, nothing more. If they were on the cluster, they would have been upgraded. And the most important property actually is the last successful release version, which specifies the name suggests itself, but I'm going to say it, the last version that the upgrade controller was able to upgrade this environment to. And if this version matches the version in the spec, the release version in the spec, so 3.2 matches 3.2, then the upgrade then the upgrade has pretty much succeeded. And now we're just very quickly going to do a validation. I'm just going to skim over this. Let's just, OK. So the node that we previously saw, now running 131.3 RK2 version. And moreover, we can see that there are no operating system packages that are in need of an update. So yay, we managed to update the packages. And for the Helm charts themselves, again, I'm just very quickly going to do this. We see that Rancher has been upgraded to 2.10.1. And we can see that its pods are running. So the upgrade was successful. We didn't just break Rancher because we don't know what we're doing. The same thing for Longhorn. It has been upgraded to the expected version. Its pods are running. And the same for the other two applications. Rancher Turtles running and the Metal Cubed application running. Essentially, that's the end of the demo. We are very happy. We have upgraded our environment. Yay. What's next? If you, can I change the slide? Fine. If you want to get even more information about the tooling that we just showcased, here are some links. The first one is the link to the GitHub project for the upgrade controller. The second one is the documentation for the upgrade controller within the SUSE Edge documentation. The third, as it states, is the system upgrade controller GitHub project, and the last one is the Helm controller GitHub project. So that's the last slide. I'm just going to leave it here, and I want to thank you for your attention, and we'll be happy to take your questions. If not now, then whatever.
And feel free to drop by
Yes.
Our technology showcase booth. We are showing this there. If you have any additional questions later, maybe tomorrow, once you tried it tonight in your hotel room, feel free to drop by and ask us. But yeah, thank you for your attention.
Thank you, guys.